Given the Taylor polynomial with an order n that's used to approximate a function f of x, and the polynomial approximation is centered around x equals a, then the remainder or error of the approximation is the absolute value of the difference between the function and the polynomial approximation. And this error is bounded by the next term in the Taylor series. So the Taylor polynomial is the partial sum of the Taylor series. So this expression on the right is the Lagrange error bound, and it's basically the next term in the Taylor series, except that the derivative is evaluated at some value c, which is between a and x. So in this example, a is equal to pi on 2, and suppose we want to approximate the function somewhere here at x equals pi. And suppose we look at the first order or linear Taylor polynomial approximation. So this here is our remainder, or the difference between f of x and the polynomial approximation. And we need to evaluate the derivative at some value between a and x, where we're making the approximation, to maximize the error bound. And we'll see that in the next examples. And if a function is decreasing, then the error bound can also be approximated using the alternating series error bound that we've seen previously. Approximate cosine pi using a second order Taylor polynomial about a equals pi on 2 and verify that the error is less than the error bound. So we take the derivatives of cosine x and evaluate them at pi on 2. And that gives the second order Taylor polynomial approximation. So the error is basically the remainder of our second order polynomial approximation. So that's the difference between the exact value of the function and our polynomial approximation. And that must be less than or equal to our error bound. So for the error bound, we evaluate the derivative of our next term at some value c, and this value c is between a and x, because we want to maximize the error bound. So our next term in the polynomial is sine c on 3 factorial by x minus pi on 2 cubed. And that's our error bound. Now to maximize the error bound, we choose c is equal to pi on 2, and then substituting for x equals pi, we obtain the following result. And if you substitute f of x and x in the polynomial approximation, you'll obtain the error, which is 0.571. So as you can see, the error is less than the error bound. Approximate the natural log of 1.3 using a third order Taylor polynomial about a equals 0 and verify that the error is less than the error bound. So here we have a Maclaurin polynomial approximation. So we need to be careful not to take our function as a natural log of 0. So we take it as a natural log of 1 plus x. So in that manner, f of 0 is equal to the natural log of 1, which is 0. And now we take the derivatives up to the third order. And evaluate these at x equals 0. And now we can write our third order Taylor polynomial approximation. And now to find the error, which is the remainder, that's the difference between a function and a polynomial approximation. And that must be less than or equal to the error bound. So for the error bound, we evaluate the derivative of our next term of the polynomial at some value c. And then multiplying this by x to the 4 on 4 factorial gives us the error bound. And in this case, x is going to be 0.3 and a equals 0, so c is between a and x. So to maximize the error bound, c is in a denominator, so we take it as 0, and x is 0.3. So if we calculate this out, and if you substitute x in the polynomial and subtract the result from the natural log of 1.3, you obtain the following result for the error, which you can see is less than the error bound. Approximate 1.3 to the 512 using a third order Maclaurin polynomial for the following function and verify that the error is less than the error bound. So this is our function, and differentiating it 3 times, and evaluating these at x equals a equals 0. So our third order Maclaurin polynomial approximation can be written as follows. So now to obtain the error in our approximation, that's the remainder. And that must be less than or equal to the error bound. Now to obtain the error bound, we obtain the derivative of the next term in the series and evaluate it at some value c. So in this case, given our function here, x must be 0.1 to obtain 1.3. So our error bound can be written as follows. So because c is in a denominator, we choose c is equal to 0 to maximize the error bound, and x is 0.1. And calculating this out, now to obtain the error, we substitute x equals 0.1 in our polynomial and subtract it from the exact value. So calculating that out, so we can see that the error is less than the error bound.